All right, today we're going to look at subsets of the complex plane. Okay, what does this mean? So the complex plane looks like this. It's the Argand diagram. Let's draw that. Here we go. We've got imaginary part of Z, real part of Z over here. Okay, so we're looking, here is all the set of the complex plane, so all the possible numbers of Z lie somewhere here. I can put a Z here, is it, any point on this plane represents a number, it's a complex number. Remember, Z is equal to X plus YI. Okay, so we're looking for a subset of these possible Zs. Okay, so we could have, all right, let's just get into an example, I think. Let's rub this out and I'll show you what I mean. Okay. All right, let's suppose we're looking for the set of Z, we're looking for a subset, so we're set of numbers Z, such that the real part of Z is equal to 3. Okay, that's our set. This is a rule for a set. All these numbers in the set are complex numbers. Let's just see what they might look like. If we get the real part equal to 3. Okay, so if the real part is equal to 3, what do we have? Well, let's look at an example. We've got 3 plus 0i right here. Okay, and we've got 3 plus 1i, 3 plus 2i. The real part is always equal to 3, so these are valid, these are part of the set Z. All right, we could have 3 minus I, 3 minus 2i, and all these numbers in between as well. And all the numbers between those numbers, we can see where this is going. We're getting every number that lies on this line belongs to this set. Okay, so this set has a Cartesian equation of x equals 3. Yeah, so a Cartesian equation for that. We get a vertical line. Vertical line. Okay, let's look at another set. Well, let's say we've got a second set, Z, such that the imaginary part of Z is equal to 2. Here's another set. So let's start plotting a few of these numbers Z where the imaginary part is equal to 2. We could have 0 plus 2i. We could have 1 plus 2i. We could have 2 plus 2i, 3 plus 2i. All these numbers. You can see where this is going. Any number along this line is part of this set. So we've got a vertical line, which has a Cartesian equation of y equals 2. Okay. Oh, did I say vertical again? I meant horizontal. Horizontal line. Right down. Okay. Wonderful. Let's get rid of this. Now, pretty easy examples. Let's do some more examples. What are we going to get for the set? Okay, we've got numbers Z such that twice the real part of Z minus 5 the imaginary part of Z equal to 1. Okay, so what's this set going to look like? Okay, so we could solve this algebraically if we wanted to. Now, if we think, all right, all complex numbers can be written as x plus yi. Okay, so the real part of Z is x, and the imaginary part of Z is y. So we've got 2x minus 5y is equal to 1. Okay. We could rearrange this a little. 5y minus 2x plus 1, which means y equals 215x minus 1/5. Okay, so all the with z are going to lie on the Cartesian equation of this. So we get, we were to draw it, we could draw it as a Cartesian equation if we wanted to. I suppose it's better because we're actually looking for these z things. You know, they're on the complex plane. Let's just keep it to the complex plane. But we know if we lay the Cartesian plane over the top, then we'd have the same thing. Okay. So 2x minus 2/5 x minus 1/5 x. Something like this. Yeah. Something like that. Yeah. Goes through. No, we won't even draw it for now. You get the idea. That's what it looks like. Yeah. Nice. Okay, so that's a linear line. This is a linear line. Cool. All right, next one. Let's have a look at the next example. Get rid of this. Okay, what have I got? We're up to circles. Yeah, let's have a look at circles. So how are we going to get a circle on the complex plane? Write that down. Circle. Circles. Okay, the way to get a circle, if we think of z being x plus yi, right? And on the complex plane, the magnitude of z gives your distance from 0, or the origin, yeah? Distance from here. So if I wanted the magnitude of z, so all z such that, in a set, that the magnitude of z is equal to 3. So I could think 3 plus 0i, 0 plus 3i, I would have negative 3, 0, or 0 minus 3i is a number. But I could also get all these numbers in here that have they're a distance of 3 from 0. So it's like you're getting a radius here. Yeah? Radius of a circle. All those points in there, oops, that's too high, give you this circle of radius 3. Okay. Now, to solve this algebraically, we're looking at the magnitude of z is equal to 3. So get the Cartesian equation. Let's the magnitude of z is the square root of x squared plus y squared. Okay, and that is equal to 3. Squaring both sides, and I get the equation of the circle. Yeah, x squared plus y squared equals 9. Wonderful. Okay, what would happen if, I might run this out again. What would happen if I had the set such that I had z minus 2 was equal to 3? What would happen to my Venn diagram? All right, let's have a look algebraically first. So if I substitute z x equals y, x plus yi for z, so I've got x plus yi, that's z, minus 2 equals 3. Okay, let's group the real bits together. So I've got x minus 2 for the real bits, minus yi equals 3. So the real bit squared, imaginary bit squared, square root, the answer. X minus 2 squared plus y squared is equal to 3, which gives me square both sides, x minus 2 squared plus y squared equals 9. So now I've got a circle of radius 3, and its center is at 2, 0. Yeah? So it moves it right 2. So this has the effect of moving right 2 units. Yeah. I could change it again. So what would you think would happen if I had the magnitude of z plus 3 minus I equals 1? Okay. So this is going to be a circle. Yeah. At center, -3, 1, moves up 1, yeah, and has a radius of 1. So I could just draw that straight on the Argand diagram. I would know the set. Good. Okay, let's move on to the next bit. Okay, what would we get in this scenario? So we've got z minus 2. I want the sets z such that the magnitude of z minus 2 is equal to the magnitude of z plus I. Okay, what's going to happen this time? Okay, the way to think about this geometrically. Okay, let's see what happens to this one. So the way I think about this one is, well, I think of the magnitudes as distances. So what I say to myself is that the distance from 2, yeah, 2 over here, has to equal the distance from -1, negative I, yeah, real part of z, imaginary part of z. Okay, so if I've got 2 over here, -1 here, then I want a z that is equal distance from these 2 points. So one easy point is the midpoint. That's a equal distance from each of them. And then if I pick a point down here, the distance down here, if I make this an isosceles triangle, has to be the same, same distance from each. So I could think of this one as the perpendicular bisector of these 2 points, of the line that joins these 2 points together. So I can draw that line in. Okay, so what is that point? Let's have a go at trying to work that one out. Okay, so I'll do it over here. So I've got the magnitude of z minus 2 has to equal the magnitude of z plus I. Okay, I'll skip a few steps here because this is going to go into the real bit. So x minus 2 all squared plus y squared equals the square root. Now this is going to go into the imaginary bit, which is the y bit. So we get y plus 1. So it's going to be x squared plus y plus 1 squared. Okay. I can square both sides, expand these brackets out. The square roots go. Expand the bracket out. Okay, this one plus 4 plus y squared has to equal x squared plus y squared plus 2y plus 1. Okay, so x squareds go, y squareds go, and I'm left with, I'm going to write this around the other way, I'm going to write the 2y first, and what am I left with on the side? 2y minus 4x, all up I've got plus 3, yeah, minus that away, yep. Okay, and then y equals -2x plus 3 on 2. Oh, it looks like a perfectly valid line here. I've got -2 as the gradient, y-intercept being 3 on 2. Perfect. Okay, let's go to the next one. What else can we have? Oh, right to the last one. Last one I want to show you is all these rays. Yeah, rays. Okay, so that would be when we've got a set of z such that the argument of z is equal to pi on 3. So if I was to draw that one up, so the argument is the angle it makes with the positive x-axis. Yeah, the angle has to be between negative pi and pi. Yeah, inclusive of pi. Okay, so the argument of z. So all the values of all these z values that have an argument of pi and 3. So we can have them all. Can't include the origin though. Can't include the origin. So it's going to be an open circle on the end of the ray. Okay, and this angle, pi and 3 degrees. Okay. So if you were going to work out the Cartesian equation here, you might try that. So the argument of z in most cases is the inverse tan of y on x, going to equal pi on 3. Okay, so that means y on x has to equal tan of pi on 3. Tan of pi on 3, that's root 3, isn't it? Yeah. And therefore, the equation is y equals root 3x. Okay, so which values is this legitimate for? Well, it's legitimate for any x value that's greater than 0. Yeah, so as long as x is, I'll write it like this, 0 to infinity, or x greater than 0 would be a perfectly easy way to write it. That would do. Okay, that's it for today.